Alright, so today's lesson is 2.6, the chain rule. 2.6 in your textbook starts on page 96 if you want to check the material there. But the chain rule, so let's set this up here. We have been talking about lots of different rules in chapter 2 about how to find the derivative, right? We talked about the constant multiple rule, like the derivative of any number that doesn't have a variable to it is just 0, right? The power rule is a big one. The derivative of 2x squared is 4x, right? So you know about that. Sum difference rule. Product rule, quotient rule. Now is another major rule called the chain rule. Now you're probably wondering why I have a picture of some sliced onions here. When I talk about the chain rule, I talk about onions, and onions are pretty famous for having layers, right? So I want you to notice in this picture right here that the onion has many layers, outside layer, then an inner layer, and it just keeps going on until you get to the center, right? So an onion has layers, and that's pretty famous for onions make you cry, and onions have layers, okay? To get to the inner layer, you have to peel out the outside layers first, okay? So, having said that, if we look at a function, so let's say a function f of x, and let's take this function for example. Now, this is x plus 1 all squared. Now, we've done a little bit of work with this, right? We've talked a little bit about composite functions. A function within another function. Where did we talk about that? Well, when we did something like this, right? F of a plus h, right? This one here. When we talk about this right here, when we're finding the limit and so on, f of a over h, right? This, a plus h, is like a function within another function. So we've seen this before, and we've kind of come through these hurdles already as a class. We've been able to put 2 plus h, let's say. If a equals 2, we know that 2 plus h has to go inside f of x function, right? And so we've kind of done this before. So a function within a function, if we think about that, and we look at this f of x then, what would be the inside function? What's the inside function here? What function has been placed inside another function? X plus 1. Good. This x plus 1 is the inside function. And the outside function is sort of this quantity here squared. Now, if we think about an onion, okay, let's just back that off a bit here. So if we think about an onion, I have the outside layer is this big function squared, right? The blob or the thing squared. That's the outside layer of the onion, and the inner layer of the onion would be this function that's actually inside. So you can kind of see how sometimes a function can be made up of several functions that are composed. So we would say that you have an outside function, inside function. Those are the terms I'm going to use. So really, this f of x, right, could be written as two different functions. The first one, the outside function, could be like a g function, okay? And the inside function may be an h function. And so this is how we might express this. So just take a moment to absorb that, if you will. Don't let it make you cry, like onions do. But I want you to see that there's a function within another function, okay? And the h of x, we already said, is x plus 1. You guys have noticed that. What about the g of x? What's the g of x function? It's, okay, well, if we're talking about the outside function, it's just x squared, isn't it? And so h of x, this x plus 1, goes inside the g of x function. So g of x is the outside function. Okay? And h of x, the inside function, is this part right here. Okay? So are we kind of understanding that you could express a function in terms of maybe two or more other functions? So let's do another example here. Let me just erase. Okay, another example, square root of 2x plus 1. So if f of x is indeed, g of h of x, where we have an outside function and inside function, which one is easier to determine, the inside function or the outside function? There's no right answer there, but I just want to know. Can you see kind of an outer function first, or do you see an inside function first? Okay, so one is not easier to see than the other. Fine. Let's take a look at h of x. What's h of x then? Okay, yes, it is. It's 2x plus 1. Now, why is it not just 2x? Okay, because it's under the root sign, but 2x is under the root sign, just the same as 2x plus 1. Why is 2x not the innermost function of everything? Let's say there's more than 2 functions. What if there's more than 2? Would 2x be an innermost function? Do you know what I mean? Okay, let me just back this up a little ways. So remember, we're talking about composite functions, so a function within a function. The reason why you were right with 2x plus 1 being the inside function, because I know you were just kind of looking at 2 different possibilities, right? Because that's what I said here. But you wouldn't go so far as to say that 2x is the innermost function, because adding 1 is not like composing. It's not like plus 1. That's not going inside of another function. It's not like another layer of the onion. So 2x and 2x plus 1, there's no function inside another function there. Okay. Now, as we move on, this will be a little bit more clear. But you're right. Let's just go back to this. You're right in saying that 2x plus 1 is our inside function. 2x plus 1. And the outside function, that's the g function, would be what? Square root of x. Very good. Okay. Very good. All right. So you're pretty good at identifying. I don't know what word that was I just said. Pretty good at identifying functions within functions. Let's talk about maybe a situation where we would have more than 2 functions. Okay, so here's another example here. Now, if we take a look at this, let's see what we can find. It doesn't matter if you look outside or inside first, but I usually start outside. And you're going to have to, using the chain rule, you're going to have to kind of start with the outside function. So I kind of look at the outside function first. And that certainly is, square root of x, or square root of something, right? So let's say g of x would be square root x. Everyone see that as the outside function? Okay. Now if you go inside that function, the next layer of the onion, you're going to look at this polynomial. And that is a polynomial, right? So that's x plus cubed root of x, or x to the 1/3, right? Okay. Now is that any different? Is this any different than this? Is that any different than that? So do we have 2 or do we have 3 layers? So what I'm suggesting is, I'm saying, do you think this is the case where we have 3 separate layers? Is this any different than this one, or yes or no? What do you think? Okay, let's keep going. H of x, the next one we said might be 1 plus cubed root of x. Okay, I would agree with that that's our next layer. My question is this another layer on top of this one? And the answer would be no, because it's the same as this. Okay, so if you have just x to the power of 1/3, it's the same as just x squared. So just as in that last example, we only have 2 layers here. Where we would have 3 layers is this. Are you ready? Here's the next one. I'm going to do something very similar. I'm going to do 3 layers. Okay. This is an example where it's a little bit different, and you can kind of see that really what we're trying to get to is this x, right? I mean, if it's just an x variable and not like an expression or something, we've kind of got to the rock bottom. So in recognizing layers here, you would have, first layer is this square root. Okay, that's the very first layer. So we have, first layer is root x. The second layer, let's do this blue, would be everything underneath that root sign, everything. The next layer down. And so, h of x would be 1 plus cubed root of, and now I'm using the same variable here, so this is where it gets a little bit iffy. Okay, it's all of x, of x, of x. But let's say gh, let's say k of x. Our last layer would be this part in here. Okay, so that's x plus 1. And then we're done. So does everyone kind of see that if I'm not substituting anything, see this x has been substituted, this whole thing is for another variable. This whole thing is for another variable, but then you've gotten down to the very core of the onion, so you're done. 3 layers. Okay, does that make sense? Okay, so as long as we got that, you guys can start to recognize that, then that's great. The chain rule itself is very easy. What you do in the chain rule is you take the derivative of the outermost layer and you multiply it by the derivative of the next layer and multiply it by the derivative of the next layer inside, and you keep going until you're done. Until you get down to just your variable, where the derivative of this would be just 1. And then you're done. So you just basically take the derivative of each layer and multiply them out. The trick is that you have to remember to only take the derivative of one layer at a time. So you can't take the derivative of all 3 layers in one step. And I'll show you how that works. It's okay. This is going to be some pretty basic examples here. So let's do this one. F of x is 5 minus 3x to the power of 7. Now before, if I've given you one like this, maybe it's been squared, right? And you have the option of showing this as a product of 2 binomials if it was squared. Or you could expand it out and do, just your sum difference and power rules. But this is where the chain rule comes in very handy because A, you're not going to want to expand this out, right? You're not going to want to multiply by itself 7 times. And B, the product rule, you've got 7 factors. So you've got a little bit of an issue there, right? It can be pretty complicated. So chain rule is going to be pretty simple. All right, so the layers. Let's go after the layers. The first layer is going to be all of this to the power of 7. Everyone see that? That's the first layer. The inside layer is then this 5 minus 3x. So there are 2 layers. 2 layers. So the derivative of this, the chain rule says I got to take the derivative of the outside layer only. So if this was, I'm going to use a different variable here, but this is the outside layer. Let's not think about this as x yet. Okay? What if I took the derivative of this? What would the derivative be of something to the power of 7? What would it be? 7 times the something, in this case it's w, to the power of 6. That's the derivative of this. Good. So that's what we're going to do to this one, but we're not going to touch this inside layer the first time around. Okay? Do not take the derivative of all of the layers at once. That's the only thing that kids get stuck up on. They get tripped up on that. So this is what we're going to do. We're going to do 7, okay, times, and I'm going to leave this alone for the first step. To the power of 7 minus 1, or 6. So do you see how we've taken the derivative of the outer layer right there? It's just the outer layer. Don't touch any of the layers underneath. Instead, what we're going to do is now we're going to start to work inside to the next layer, and I'm going to multiply by the derivative of that layer next. So the inner function here is 5 minus 3x. What's the derivative of 5 minus 3x? Negative 3. Very good. And so simplified, this answer is 7. That's just a factor. Negative 3 is just a factor, so negative 21 times 5 minus 3x, all to the 6. Okay, so just take some time to absorb that. It looks easy, I know, but you'd be surprised when you start doing it how many times kids are going, hey, I can't put 5 minus 3 in here. I got to just put minus 3 in there. well, then you don't have a variable, which is a problem in your final answer. Okay, so layers. Questions about that one? Outside layer, inside layer. Yep, that's it. Let's do one. Let's do one together where we can do the derivative a different way, a way that you already know. So let's do something a little even simpler here. Let's go. Let's do 2x minus 1 squared. Okay, let's do that one. We're going to do this first of all. We're going to rewrite this as an expanded form. Okay. So that's going to be 4x squared minus 4x plus 1. So if I took the derivative of this, right, here's f of x. If I took the derivative the old way, just using the sum difference and power rules, we would have what? 8x minus 4? That sound about right? Okay. All right, which actually can be factored down to 4 times 2x minus 1, right? That's really what that could be simplified to. So let's go back over here to the chain rule, and the chain rule says we have to take the derivative of the outside layer, which is the blob squared. So let's take care of that first. And I don't know why, but I'm just going to write this f of x. So the derivative now is 2, bring that down, just power rule. We're going to leave this all alone in here. Subtract 1 there is just to the power of 1. Okay, so that's the derivative of the outside layer, leaving the inside layer alone. Now we're going to multiply by the derivative of what's inside, which is what? 2. Are you seeing now how if we simplify this, that's 4 times 2x minus 1, or 8x minus 4. Okay? So you see we get the same answers there. Chain rule. Derivative of the outside times the derivative of the inside. Questions? So in summarizing the chain rule here, this is right from your textbook. So the chain rule says this. If you have, now let's just kind of skip ahead. Here's f of x, and if it can be written as a composite function between, two other functions. So this is actually capital F, so we've got little f and g of x, right? So if this can be written like this, and the derivatives of g and of f, if they exist, okay, which they will for most of these examples we're going to do, so it will not be an issue, and we have a composite function like this, then the chain rule states that the derivative of f of g of x is the derivative of f. Notice that this is just regular g of x inside, so it's the derivative of x, a derivative of f with respect to g of x, so it's just g of x stays. Then you multiply by the derivative of the inside function. Okay? So it's the derivative of the outside function times the derivative of the inside function. And that's what it looks like in this notation. I'm going to talk about Leibniz notation as well here in a second. So the question was, what if we have 3 functions? Then yes, you take the derivative of the outside function and you leave everything alone inside. Right? Derivative of that one. Then you multiply by the derivative of the next inner layer with everything else left inside alone. And then you multiply by the derivative of the last layer. So it looks, just like that. So you're taking the derivative of every layer just once. In this case, f, g, and h. So f prime multiplied by g of prime multiplied by h of prime. Do not see, we don't have h of prime in here, and here, right? So it's just, remember that the inside functions are left completely alone, and then that way, you're going to get to your correct answer. Okay? The chain rule, outside layer, inside layer, multiply the derivatives. So let's get some more practice. So here's an example for you. Take the derivative of x squared minus x plus 2 all to the power of 8. Go ahead and give that a try, and I'll show you the answer in a minute. Okay, so the derivative of the outside layer, that's the function to the power of 8. So bring the 8 down, leave everything alone on the inside, multiply by the derivative of the inside, which is 2x minus 1. And then, as I mentioned, you can leave it in factored form. Don't expand anything out. Okay, you don't have to. Leave it in factored form, and it wouldn't really matter which way you write these factors. I would actually tend to do this, but it doesn't really matter which order. I'm not really worried about that right now. It doesn't really matter. Okay? Usually you have this number, if it's just a constant number as a factor, you usually have that one first, but other than that, it's okay. Okay, questions on that one? So for this example here, this is going to be the chain rule. So we have an outside function here, and then we have the quotient rule inside. So here's your outside layer, and then your inside layer, which you have to use the quotient rule for. Okay? So go ahead and find g prime of x here. And like I say, you don't have to expand anything. You can leave it in factored form, but simplify the numerator denominator if possible, writing in factored form. Okay, give it a try, and we'll talk about it in a minute here. So here's the worked out solution. I'll just kind of walk through what I did, and then you can tell me whether you did the same thing. So it looks like this. The outside function, as I mentioned, was that the inside function here. It's this thing cubed, right? It's something cubed, and so we do 3 times this inside function. Leave it alone. Squared. Then you do the quotient rule on this, and derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. You simplify this over here, the x's cancel out, and you get a negative 4 on top. Now notice that when you get to this point right here, if you left it there, okay, so-so. The best would be to recognize that we have an x, minus 2 all squared in the denominator here, and an x minus 2 all squared in the denominator here. So you should combine that to make this x minus 2 all to the 4th. And of course we just have a constant as a factor and another constant as a factor, so you should combine those. So this would be your answer. That would be your simplified answer using the chain rule and the quotient rule there. And I'll just flip over to your solution manual. Now this may or may not help you, but this is what it would look like if you come up and check your answer back, which is right here. Alright, so then see that? So you got 3 times this all squared, and then times this up here, and they jump right to the simplification there. So there's your answer right here. Same as what we got.